Dear students, welcome to this video number 7 on simultaneous fault. In this video, we shall deal with the simultaneous faults, that is Z type of fault, Y type of fault and H type of fault. And this is our learning outcome number 4. Now before going to simultaneous fault analysis, let us have some understanding of prerequisite for simultaneous fault. So already we know that unsymmetrical fault. So uh, so here I have listed all the unsymmetrical fault. So the first one is LG fault, line to ground fault, then line to line fault, then line ground fault. And these three faults, they are called as shunt type of faults. And then we have one conductor open and two conductor open. These faults, they are called as series type of faults. So these things already we have learned. Now when such a fault is taken place in the power system, then how to do the fault analysis? So whenever we are dealing with unsymmetrical fault, as we discussed in the class, that we require three sequence networks. So one is positive sequence network, negative sequence network and zero sequence network. And depending on the type of fault, then we are connecting these sequence networks in series or parallel combination. So let us say that, let us first look at the LG fault. For if there is a LG fault, I will take one generator. So to understand this, suppose there is a generator and suppose the fault is occurred at its terminal, that is LG fault. I am taking now LG fault. Now I want to find out what is the fault current and what is the voltage, uh, everything. So I will first get the positive sequence network of the generator. So now positive sequence, so we will have a reactance. So these reactance may be either transient reactance or subtransient reactance depending on the requirement, and we will have, this is the uh, voltage, what we call it as voltage behind transient reactance or subtransient reactance. So this is we call it as say Z1, that is positive sequence reactance, and now this is the current IA1, that is, and VA1 is the voltage with plus and minus. So this is positive sequence network. Then for the same system we draw negative sequence network. Now for the present system where we have considered only generator, so our negative sequence network will be like this. This will be IA2 and the voltage is VA2. Similarly, for this network we can have a zero sequence network also. So Z0 is this zero sequence reactance, I0 is the zero sequence current, V0 is the zero sequence voltage. Now after getting this positive, negative and zero sequence network. Now for LG fault, I'm talking about LG fault. For LG fault, already we learned that these network should be connected in series. They should be connected in series like this. And then we can find the current I1, I2 and I2, I0. And from these sequence currents, we can find the actual current with the fault. So this is how just I'm revising the previous learning. So uh, 1 minute, I'll just okay. So here I have drawn the table for LG fault. The diagram you can see here in the diagram, all sequence networks. So this is positive, this is negative and zero sequence network. They are all connected in series, and here we are not consider any fault impedance. But if there is a fault impedance, then we are including that impedance as 3ZF over here. So the connection for LG fault, it has to be understood here. What is the point to be noted? That for LG fault, positive, negative and zero sequence network, they are connected in series. Okay. Now similarly, if you go to two conductor open, now I have taken here series type of fault. For two conductor open, you can see here that this is positive sequence, this is negative and zero sequence network. They are also connected to be connected in series. They are to be connected in series. So here I1, this I1, I2 and I0, they are the sequence currents that flowing that flows out of the fault, and V dash 1, V dash 2, V dash A, they are the sequence components of the voltage across the fault. So here you have to remember that for LG fault and two conductor open, positive, negative and zero, they are connected in series. Okay, now let us go to this. Okay, now here for LLG fault, there is line to line ground fault. You can see here this is positive sequence network, this is negative and zero sequence network. They should be connected in parallel. Okay, then one conductor open, if one of the conductor gets open, then the three networks positive, negative and zero, they should be connected also in parallel. Okay, so we have this combination like LG, two conductor open, two conductor open, the networks are connected in series, and for LLG and one conductor open, the networks are connected in parallel. So this is to be noted here in this prerequisite. Okay, now we shall go to, let's start with now our actual simultaneous fault. The first type of fault here it is taken is Z type of fault. Here it is taken Z type of fault. This fault is also called as series connection. Now why it is called series connection, we will try to understand here. So now this is the way we should write in the exam also. So it is used to analyze following type of faults. So to LG fault at ith and jth bus. Suppose you have a power system and I have two bus, say I and jth bus. And now suppose at this point there is a LG fault. LG fault means what? We have seen the networks, they are connected in series. And at the receiving end, at the jth bus, there is also LG fault. And we know that for LG fault, the sequence networks, they are connected in series. So whenever LG fault, so two LG fault are taken place at ith and jth bus simultaneously, then it is called as Z type of fault. Now why it is called series, you understood. So there is a LG fault for which there is a series connection of sequence networks. There is also a LG fault at another location. For that also sequence networks are connected in series. So it is called a series connection. Next one is LG fault at ith bus. Suppose here at this point, so suppose here LG fault is taken place at ith bus and two conductor open fault at jth bus. Now here LG fault is not taken place at this bus. You have two conductor open. You have two conductor fault. So you can see that at one you have LG fault, at jth bus you have two conductor. But for LG, we know that the connection is series, and for two conductor the connection is also series. So it is still series. So it is called as Z type of fault. Then two conductor open, two conductor faults at ith and at ith bus and LG fault at jth bus. Now they are reversed. Means what? Suppose you have ith bus and you have jth bus. Now here you have two conductor open fault and here we have LG fault, but still they are series because for two conductors still your sequence network connected are series, and for LG also your networks are connected in series, so still it is series type of fault, that is Z type of fault. Then we have two conductor open faults. So two conductor fault at ith and jth bus. So suppose if I have a ith bus and then we have a jth bus, and at the both the buses we have two conductor open. Then still it is series type of fault, that is Z type of fault. So in the exam you have to write, if they ask you Z type of fault, then you should write it is series connection and it is used to analyze the following type of faults. Now let us look at this network. Now figure shows the sequence network connection for Z type of fault. Now here is very important point to be noted. Now let us understand this. What is this positive sequence network? Okay. Now uh, suppose you have a power system. Okay, I take one power system and there is a line or there is a bus, say ith bus, and there is a bus called jth bus. And now say LG fault is occurred at this point, LG fault, and also there is here LG fault taken place simultaneously. Now my objective is to find the voltage at this point and the current at this point. What is the voltage at this point? So I will call it as VI, II, VJ and IG. Now I am interested only in these four parameters. Oh, four parameters are Vi. Let us understand this. What is Vi? Vi is the voltage at the ith bus where the fault is taken place. II is current at the, this is the fault current. This is the fault current. Okay. Now suppose I now consider that there are three lines, and I will take it here. It has A line, B line, and C line. Now the fault is taken at LG fault. LG fault is taken at the ith bus, and also the LG fault is also taken at at the same, at both the locations. It is taken on line A only. Okay, let us start with that. But there is a possibility that LG fault may occur at A, and at another look at jth bus it may happen on B bus or C bus, like that. So that different combinations. But let us start with both the faults, they are happening on line A. Now what is my objective? My objective is this: to find voltage at ith bus, current at ith bus, voltage at jth bus, and current at jth bus. Okay, so this is my objective. Now how to do that? Now what you do, because you have only four parameters of interest, so now we can have two port network concept here. So what we can do, seen from the fault point here, that is, here we have 2 points, here we have uh, you know seen from this location, this is, you can take it as input port where the fault is taken place, and here you can take it as output port where the another LG fault is taken place. And now seen from these two, look at this as two ports, two pay terminals. So this is what you can say, uh, this is this is your input port where one LG fault is taken place, and this is the output port where another LG fault is taken place. Now you can have, for this network you have to have three sequence networks: so positive, negative, and zero. So what this positive sequence indicates here, so this is the positive sequence network of the system with input pair. This is, here you have input pair where one LG fault is taking place, and at this point this is the output port where another LG fault is taking. So similarly you can have negative sequence network and zero sequence network. Okay, so you have to understand this aspect. Now they are all connected in series, so positive, negative, and zero sequence, they are connected in series. You can see over here. So this is Vx1, Vx2, this is Vx0. So these are the voltages at the faulted point, sequence voltages at the faulted point, and they are all connected in series. They are all connected in series to get the voltage Vx at the faulted point. Okay. Similarly, here on the another output side, similarly, these sequence network, they are connected in series. So you can have here Vy1, Vy2, Vy3. They are the sequence voltages at the fault point, and after adding that, we get the actual voltage. We get the actual voltage at that faulting point. Okay, so this is what is the concept used here. Okay. Now let us write some set of equations. Equations, let us start with the one first. Now, equation to find positive sequence voltage at ith and jth bus is, so now what I'm doing, I'm finding this voltage and this voltage. So this voltage, it is taken as Vx1, and this voltage, it is taken as Vy1. That is voltage at the faulted point X, positive sequence, voltage at the yth point, positive sequence voltage. Now what is the equation? So the equation is Vi1 Vj1 equal to Ei1 Vj1 minus Zii1. Uh, this is the input impedance of the network seen from the fault point X, and this is the transfer impedance between the two fault locations X and Y. And now I will just explain this term what we hear. Okay, so now this is EI. Suppose uh, you have ith bus and jth bus, and suppose this is X point where LG fault is taken place, and this is Y where another LG fault is taken place. Okay. Now EI1, you can say EI1. Here EI1 is the voltage at this. This is pre-fault voltage. You can say this pre-fault voltage. This is pre-fault voltage at the ith bus, and EJ1 is the pre-fault voltage at the jth bus before fault. Then after fault, what is the positive sequence voltage at that bus? So Vi1 is equal to, so to pre-fault you have to add, to pre-fault voltage you have to add the change in the voltage at the bus, and this delta ei, it is find out from this it is can be find out from the Thevenin passive network of the positive sequence network. So this into this, actually this is equal to delta vi, and this is delta vj. So you can take it as 1, this is 1. Okay, so this is the change in the voltage at the ith bus due to fault, and this is the change in the voltage at the jth bus positive sequence network. So when you add pre-fault voltage plus this, now why this negative is over here? Because actually when the fault is taken place at this point, the current comes out of the fault. But in the two-port network, we can see that in the two-port network, in the two-port network, we take current in this direction. It is input current. But actually, the current, the fault current comes in the negative direction. So the minus sign is accommodated into this current vector. Okay. So this is the equation to find positive sequence voltage at ith and jth bus. Okay. Then also from figure we can write here, now this transformer, actually this is not to be considered as transformer, this is just to accommodate the on which line the fault is taken place. Okay, that means what? Now suppose you have three lines A, B, C, and suppose LG fault is taken place on on the A bus, and also LG fault is taken on the A bus in the jth bus. Uh, Now, in that case, this transformation ratio, this is Ni1, it is written as Ni1, it will be 1. So it will be 1 raised to 1. It will be 1 raised to 1. Now suppose if the fault is suppose if that if on this side the fault is taken place on VB. Now in positive sequence voltage we know that suppose this is VA1 and this is VB1 and VC1. Now you are interested in VB1, not VA1. But how to convert VA1 to VB1? So you have to multiply this by alpha square. I think yeah, alpha square. So you have to rotate this vector in the positive direction by alpha square. Alpha is 1 at an angle 120. So this Ni1 in this case, so this Ni1 it will be alpha square. So your transformation ratio will be taken, so depending on which line the fault is taken place, so accordingly we can choose this transformation ratio, whether it is alpha or whether it is alpha square. Now here we get, so here it is written the equations. So Nik means now Ni1 or maybe Ni2 or something like that. So it is Vxk divided by Vik. Vxk, it is the the voltage at the sequence voltage at the faulted bus. Okay, and this is in you know uh, this is you are taking it as reference. A bus is taken as reference bus. Now if the fault is taken on B bus, then accordingly we have to accommodate that what you can say, multiplication of alpha square, we have to take care of that. Okay, so this is on the output side, this is on the output port side. So this is the transformation ratio NGK. Now substituting, now what we are doing here, we are substituting this into this equation. So we are substituting, for all the things, like we are substituting for II1. So II1, Ij1, Vi1 and Vj1. We are substituting in terms of Nik and Njk in this equation. So what we get? We get this equation. So I think for everything we are substituting. Um, yeah, we are so then we get this equation. So here you can see this transformation ratio has come into picture. Okay, and here you have Ni1, this is Ni1, this is Zij1, this is Nj1, this is Zji1, this is Zjj1, Ixi. Okay, now this is what we have obtained here. This is, we have obtained the positive sequence voltage at the ith and jth bus. Okay, similarly, uh, equation to find negative sequence voltage. So negative sequence voltage, as already I told, now now this here, now this term will not come, into negative sequence voltage. Why? Because pre-fault voltage, so at the fault point the pre-fault voltage will be zero, that is, there is no negative sequence voltage before the fault. So that's why this part will be zero in the negative sequence voltage. So we can see over here, so only you can have this change in the voltage. So this gives you change in the voltage at the ith bus and jth bus. Okay, so this is negative sequence voltage equation. Similarly, you can have zero sequence voltage. Here also the pre-fault voltage is zero. No zero sequence voltage will be there in the system before the fault, and that's why you will not have that pre-fault voltage vector, and this matrix into this matrix will give you the change in the voltage at that bus. Now you have to add, but what is the constant equation? So already we have seen that all positive, negative and 0, they are all connected in series. They are all connected in series. So we have to add this voltage. So here it is written, this is positive sequence voltage, negative sequence voltage and zero sequence voltage. They have to be added because they are series connection. So after combining Uh, okay, substituting, so combining all equations A, B, C, then we will get the combined equation for Vx and Vi. Vx and Vi are the voltages at the ith and jth bus, and after adding all the terms, we will get this. This is the complete two-port network model for the three sequence network connected in series. So what is ZII? ZII is ZII plus ZII to ZII 0. So it is sum of the sequence impedances. So similarly ZIJ and Zij and Zjj. If you combine those equations, then we will get these equations Zii, Zij, Zij and Zj. So I will not do that work over here, but separately you work on that and you can see that you will get this two-port model for for interconnection of three sequence networks connected in series for Z type of fault. So, okay, so in the next video I will take up Y type of fault and H type of fault in the similar fashion. Okay, up to this only in this video. Thank you very much.